Hello everyone, this is B9 and welcome to my channel. The theme of today's lesson will be about dot product, this kind of basic vector math operation that in Houdini world is used almost everywhere, and it's like usually the students are being taught about it on one of the first lessons, and once you understand it, you start using it everywhere. But I checked what is happening in the Blender world, and there are a couple of tutorials about that product, but all of them start with boring and very long and super hard to understand some kind of diagrams without showing you exactly why you need to know it, what is the practical purpose and helpfulness of this operation. And today I want to demystify dot product in the Blender world. And for that reason, I prepared a couple of examples. For example, this one, the extrusion is based on the dot product. There is completely different example where we do camera culling. As you can see, we go from 38,000 of instances to 22,000 without visually changing much. And we calculate what to delete also with the dot product. And the last one is this, where we use, we use a dot product to detect what points are inside of some arbitrary geometry. So as you can see, dot product can be used in variety of situations, producing completely different results, and it is super helpful for the geometric operations. So unfortunately, I have to start also with the diagram, but I want to make it super quick and just explain you the basics very, very quickly. So let's go. If we have a look at the dot product node in Blender, you can see that we have two vectors as an input and some float value as an output. And let's quickly talk about what does it mean. Let's take a brush. So let's say we have vector 1, and some vector 2. Vector 2, and I'm gonna draw another vector. It's vector 3, somewhere here. So when we plug these two vectors into the dot product, we get some float value, which will tell us if these two vectors are pointing into the same direction, and if so, how much. And if we have a vector that is exactly the same as the second one, we get dot product value as 1. And if we get some vector that is completely the opposite, pointing the opposite direction, the dot product will be -1. And for the vectors in between these two, we will get value ranging from -1 and 1. And somewhere in the middle will be value of 0, which is very handy because if we say that if we get dot product somewhere between 0 and 1, so positive, it means that the two input vectors are pointing into the same direction. And if we get dot product between 0 and -1, it basically means that these two vectors that we plug in are pointing the opposite direction. And you can start filtering, do the greater than and all this stuff, comparing these two vectors. And it's this simple. There is nothing more about dot product that you need to know. So how much it took? 1 minute or 30 seconds to explain? That's it. We can jump to the practical examples. We don't need to speak about this anymore. So let's go to the practical examples. We will start with this first example where we will be using dot product to detect if the point is inside of some geometry or not. And this will drive the change of color and also changing of the shape. And we can start moving this geometry around and the algorithm will be working. And I want to explain first how we're gonna do this with some quick diagram. Let's say we have a bunch of points scattered. And we have some geometry. Let's change the color to something else. And what we can do quickly is use raycast node to throw some rays into completely random direction, for example like this. And then we can compare this direction to the surface normal of the geometry. And if these two vectors are more or less pointing to the same direction, basically the dot product between them is higher than 0, it means that we are inside of the geometry. Because let's draw some another point. Because if we send the same ray from this point into the same direction, the normal will be pointing the opposite direction. So the dot product between these two vectors will be below 0. So this way we can use dot product to do the detection. So let's jump back to Blender and start assembling this scene. I'm starting here with the empty Blender scene, and I have enabled screencast keys so you can see what I'm pressing on the keyboard. So let's delete the camera because we don't need it, and let's select our cube and create new geometry node modifier. We will cut the connection and make some room. First things first, we need to scatter some points inside of this cube, so we will do mesh to volume and instance distribute points in volume. Let's plug everything together and we should get some points, and we can increase the density so we get more points. Second thing we will need is some geometry that we will use to detect if our points are inside. So I'm gonna create a monkey and move this monkey a bit to the side, and we're gonna pin the geometry node so it doesn't get disappearing all the time. We select something else in the viewport. So right now we have our monkey and we have our points, and some of the points are inside of this monkey and some of them are outside. So how can we tell? Pretty easy. First, let's bring the monkey and switch it to the relative. And pretty easy, we can use raycast node. So we plug our target geometry as a monkey as a target geometry. Let's get out our vector because we will need to use it. And all we have to do is compare the normal with the vector that we are shooting rays to. And helpfully, this raycast node already has the normal, so we don't have to read any attributes. We can just use this socket. So let's do dot product. And we can plug our normal with our vector. And if these two are pointing more or less into the same direction, it means that the point is inside of the geometry. How can we check this? With the compare node. Compare, and all we have to know if the dot product is greater than 0, and we get our points. We can quickly check it with separate geometry node. If we plug our result here, yes, the first input gives us the points that are inside of the geometry, and we can start moving our monkey to see if it's updated, and it is. But instead of using a separate geometry node, we can use one instance node and we will instance two different geometries in it. So we can go to instance on points. Let's plug our points. Let's plug our output into the viewer. And what's cool is that this instance is a multi-input, and there is also pick instance option, and you can plug instance index, basically 0, 1 for each point, or etc. We will create a cube and a cone, and we will use geometry to instance node to merge these two together, and we will plug them into instance input. Let's adjust our scale with the value node. And we can use this as our index because we only have two geometries and this is producing zeros and ones. So if we plug it here, and click pick. We get what we wanted. Everything that is outside of the monkey is cube, and everything else that is inside of the monkey is cone. And we can start moving it around to see the result. What will be helpful is to change this monkey into the wire display in the viewport, so we can visualize it more easily. So we can start moving it around, and more points turned into cones. And it is that simple. Again, how much time it took? 1 minute, 2 minutes? That's it. Let's switch to the next example. This time I'm not starting with empty scene, but I prepared some geometry, so to speed things up. I have a plane that I have some displace modifier applied to. That it will be our terrain. And I also modeled this cheap and dirty tree that we will be scattering. And we will use default cube as a holder for our geometry node setup. So we can start. Let's create geometry nodes modifier. Let's cut the connection. And we need to bring our terrain, our tree, and our camera into the geometry node setup. And let's put them side by side. And let's switch all of them to the relative mode. So we will start by scattering some points on the terrain. So we can use distribute points on faces. Let's take our plane as a mesh. Oh, sorry. And let's see what we get. Yeah, we have some points. And then we will be instancing trees. Instance on points. Let's take our tree, let's collapse it, and let's plug it here. And we have crazy number of trees. We can adjust the scale with the value node. Let's put 0.6 maybe, or even less, 0.4. Yeah, something like this. This is our crazy big forest. And then we want to delete some points on the surfaces that are not visible to the camera. Actually, it's quite easy. So we will take our camera and let's do some theory. Let's say we have some, oops. Let's say we have some terrain and we have some camera over here. And we want to not scatter anything on the surfaces that are not visible to the camera, basically somewhere here on this slope. And what we can do is to build some ray towards this area and then compare this. Let's try to make it a little smaller. Yes. And then we can compare these two vectors. And if they are pointing into the same direction, it means that we don't need this area. We don't need to scatter on these points. And how we can build this vector? How can we shoot this ray? It's pretty easy. To build a vector between 2 points, you need to subtract position of first point from you need to subtract position of the second point from the position of the first point, and it will give you the vector between these 2 points. The only thing we have to note is that the length of this normal and the vector we just built will be different, because this vector will have a length of the distance between these 2 points, and we need to basically normalize it so both vectors are same length, which is unit length. And this is actually what a normalize operation is for. So let's go to the Blender and let's build our setup. So we need a position field. We have a position of the camera in this object info node in the location socket, and we need to subtract vector math, subtract one from another. What is this node? Subtract vector math. And then we need to normalize this vector as we discussed. And then we can do dot product. You might be wondering, where are we getting the normal? And the answer is pretty obvious. The distribute points on faces node has a normal output, which is giving you the normal of the position where the point was scattered, and it's normal of the geometry it was scattered on. So we can use this. Let's make some room. So here we have dot product, and then we can compare it to some value. And we can use output for the selection. And I think we need to use less than. And it's how you can tell what you need to use. Basically, it's based on the direction of the vector that we built, or basically the order of this subtraction. And the easiest way to determine this is set it to 0, and from the camera view, it has to be looking the same as before. But if we move away from the camera, we can see that we deleted a lot of points. So we optimized our setup pretty much. And what's cool is that it's dependent on the camera, so you can start moving this camera everywhere. The bonus to optimize things a bit further, we will also build a camera culling algorithm also based on the camera frustrum. So everything that is not visible to the camera will be deleted. Usually in the production, you combine these two setups with the dot product deletion and also deleting everything that is outside of the camera. How we're gonna do this? Pretty easy. We'll be using what is called normalized device coordinates. I will build a quick diagram. So let's say we have our screen, our camera view, and we can transform position of every point that is visible to the camera window coordinates, basically a 2D vector. And in the middle, it will be 0. And this is our coordinate system. And at the edge of the screen, it will be 1. Or on this side, it will be -1. And same goes here, 1 and -1. And then we can filter all the coordinates of the points that are higher than this, basically 1. So everything for the, let's say that we have a point here whose coordinates will be like 2 and 5. Actually, the other way around, 5 and 2. And we can delete this point because of the coordinates are higher than certain value. And then we can control how much of the gap we have outside of the camera window, because deleting everything right to the edge is not really good, because some point could be right on the edge and part of its geometry will be getting into the screen, or you want to have some overscan or whatever. So keeping this gap is always helpful. So let's just do this. We already have our camera, and we also need a camera info node. And we need to use the same camera here. It gives us this projection matrix. So first step is to invert transformation matrix of the camera. And then we need to transform point into the coordinate system of the camera with this inverted matrix. And then we will use project point node to project it using the projection matrix of our camera of new coordinate system. And then we will need to do absolute vector mat absolute to get rid of these negative values, so they are all positive, because we don't care if it's -1 as long as it is 1. And then we will do separate xyz, and we need to read the maximum between x and y, because if one of the coordinates is outside of our selected field range, we need to delete it. So we will do maximum. Yes. Sorry. Maximum between the x and y. Z is empty because we have a 2D vector here. And then we can just do greater than. And if we did all good, if we plug it here instead of selection, we have our camera culling algorithm. But I guess we need to invert it. Less than. And this is the threshold. It should be 1 or slightly bigger, just to have the gap. And all we have to do is to join these two conditions, and we can do this with the OR node that will merge two Boolean values. Since this one is inverted, we need to do not, no, and, yes, and. And there we have it. As you can see, if we unplug this, this visually almost nothing is changing, but behind the scenes a lot is changing because we get much less instances. Sorry. So here it is, your pretty cheap camera culling algorithm. And this is interactive, so we can start moving the camera and it will keep updating. The only downside of this algorithm is if something is casting a shadow into the frame but is outside of the frame, or something is reflecting stuff that is outside of the frame, then you cannot use it because you need to keep the off-camera stuff. But if you don't have it, it's really good. Use it for the environments. So the last example, I think it will be the easiest after all the previous ones. We will be making this setup, which is fairly simple. So let's go to the geometry nodes. We will again enable the screencast keys. And let's create new geometry nodes modifier. And we will be turning this cube into the sphere, icosphere. Let's check how it looks. And let's increase subdivisions. Maybe 6. Oh, it's a bit too much. Let's do 4. Yes. And then we will be using extrude node, extrude mesh. And we will be controlling our extrusion based on the dot product. And what dot product we will be using? Pretty simple. We will be casting dot product from the camera position to the geometry, and then comparing it to the normal of our original mesh. And based on that, we will be deciding how much to extrude it. So we will be needing our camera here. Again, relative, and we need to build this vector, but we already know how to do it. We can grab the position field and subtract our location, but we need to vector node. Location. And we need to normalize it. Because the length of it will be the distance between these 2 points. And we will do dot product between this vector and the normal. And this will drive our extrusion. We can test it. And it kind of works, but we need to fiddle with the values, so we can use map range. We know that our dot product goes from -1 to 1, so I can put this here. And yeah, and 1 we can keep. And here is the cool thing. We can create empty, parent our camera to this empty, and then we can do some animation of this. So the camera rotates around our sphere. So let's select it. Let's put the keyframe with I. And let's go to frame 100. Or maybe let's have 360 frames. And let's go to the last one. And let's put 360 and set the keyframe. And the only thing we have to do is make it linear, so there is no easing in and easing out. And our camera is rotating around the sphere, and the extrusion is changing every frame because dot product is being recalculated every frame. And we can make things a bit more interesting by incorporating some noise texture, and we can multiply, for example, this noise, the range of it. Nice. And then we can play with the scale, with the roughness. And we can also remap this noise. Since it's all normalized, it goes from 0 to 1, and we can increase it. And we can also power it, so there is more contrast. I hope you liked this video. What I wanted to illustrate is how much different things you can do with one setup, one vector math operation. We saw today how we can do some procedural animation, how we can optimize the scene, or how you can do some practical stuff by detecting what's inside or outside some geometry. All of it was done with the dot product, very simple math operation. So I hope you liked it. And as always, subscribe to this channel and write in the comments if you like it. And I'm still learning how to make these videos, so any feedback will be very helpful, especially about the sound, about the production, sound, about the production quality, about the editing, and about the whole dramaturgy, let's say, of the tutorial. I really would appreciate some feedback, because it's not nice to speak to some vacuum. It's always good to speak to some audience. So let me know. And don't forget to like to this video. Thank you. Until the next time. Bye bye.